All right, so today we're going to keep working through the right at 9 a.m. It's so weird. Okay, so today we're going to keep working through lecture sets number 3. So just as I had 2 questions that came in this morning. One question was about question 8 on assignment 2. So I'm going to talk about that just to give a hint regarding that question, mainly just how to set it up. The other question was about an extension. So just in general, I don't give extensions to the whole class because one student asked for it. That doesn't really make sense to me. But that being said, I'm happy to just extend the assignment till Monday if you guys would prefer. It doesn't really make a difference at this point because we're going into the reading week anyways. So if you need a few extra days, that's fine. And I'll just change the date on CrowdMark. So if you want to take the weekend to work on it, you can. And if you want to be done with it, then be done with it, right? So I'll change the due date on CrowdMark, and then I'll still talk about question 8 on assignment 2. And just before I do that, I just want to review what we did last class, because it just sets up what we're going to work towards today. So as a quick refresher, on Wednesday, we worked towards addressing 2 major topics within the realm of stratified random sampling. So just as an even more general reminder, stratified random sampling is an approach where the goal is the same as simple random sampling. So in both simple random sampling and stratified random sampling, we want to estimate some population quantity. So this could be a mean, a total, or a proportion. It could be something else as well. I mean, if you could certainly use your studies to estimate, say, the population variance, but typically we don't focus on this kind of estimation. We focus on mean, total, and proportion. But you could theoretically estimate the variance and compute an interval for the variance. Like, these are techniques that we can employ as statisticians. With simple random sampling, we collect one sample, and from that sample, we build an estimate for a population quantity. With stratified random sampling, we effectively collect H samples, and each of those samples are simple random samples. So to be perfectly clear, we have capital H, simple random samples. And each simple random sample will ideally come from a different part of the population of interest. And as we established last class, what would be even more ideal is if each of these samples, so from each of the different strata, our samples have a very small variance, but the means are quite far apart. So we would like the strata to be, in that sense, different from one another. So that way that we can be assured that we're collecting from different parts of the population, and we're getting hopefully a better representation of the overall structure of the population, because we're not risking, let's say, collecting too much information from one of these strata if we were to sort of simple random sample across all 3 or all capital H strata at once. All right, now from a more technical standpoint, just like with simple random sampling, we need to have a method in place for determining how many observations we need to collect in order to obtain a certain bound. And we need to determine how many of the observations that we collect for the entire study should go into each strata. Now, the way that we do this depends on the amount of information that we have beforehand. So one of the methods that we talked about was proportional allocation. And when we utilize proportional allocation, we are essentially just saying, given the population information, so you have some population size, capital N, and then you know how many values from the population belong to each of the different strata. That would be the capital N subscript little h. We will allocate observations in our sample, or we will collect a number of observations from each strata such that the sample proportions of each strata mimic exactly the population proportions of each strata. So if we use this proportional allocation strategy, we require the population information, first of all. And under this approach, we can also show that the variance of our estimator is going to have its own form, which is the equation given on slide 819 in equation 1. Okay. Now this equation here, which I've copied and pasted to a later slide, so I'll refer to this again. But this equation here is the first part of what we need for question 8. So we are going to take this equation, and from it, we are going to subtract off the variance under optimal allocation and show that it has the form that's given in question 8 on the assignment. So this is our variance equation, the first part of question 8. And this is the equation that we have for the variance of our mean estimate when we use proportional allocation. So when we collect a number of samples or a number of observations from each strata such that the sample proportions from each strata will be exactly equal to the population proportions from each strata. Okay, now in more general cases, we can show that our calculations for sample size and our method for allocation can be informed by the variation within the strata and the cost that is associated with achieving and the cost that is associated with collecting observations from each strata. This would probably be considered the most complicated formula that we're going to see for sample size collection in the stratified approach. And last class, we worked through a fairly simple example where taking the cost and the variations, we worked out the optimal sample size for the experiment, and then we showed how we would allocate the sample size, or how we would then and then we calculated how many observations we would take from each strata based off of these previous calculations. So we have the idea of proportional allocation. We have the idea of allocation and sample size collection under or when you have variation and cost, when you have the values for variation and cost for each of the strata. And then the last approach that we started to talk about was that of optimal allocation. And optimal allocation is an approach where we consider the costs to be equivalent across each strata. All right, so 3 approaches for sample size collection, for sample size calculation, and for allocation of the sample size to the strata. There's proportional allocation, which is the situation where given some sample size, you would simply collect a number of observations from each strata such that the proportion of observations from each strata in your sample is exactly the same as the proportion of population observations from each strata. Then there is sort of the general calculation where we calculate sample size and we allocate the sample size based off of cost associated with each variable and with each strata and the variance. And then there is optimal allocation, where we assume that cost is equivalent across all the strata. And and by using a Lagrange multiplier, we can show that the sample size that is associated with these calculations are little n is equal to W1, which is the population weight for each strata, multiplied by sigma 1, which would be the population standard deviation, divided by the square root of lambda, where lambda is given by the formula below. And then we have each NH is going to be basically just a ratio of WH, which is the population proportion for each strata, multiplied by sigma H divided by that sum times N. So under optimal allocation, we can show again the same solution. So simply that the number of observations that belong to each strata or that we would collect from each strata is basically just a ratio of the population allocation fraction or the population weight of observations in each strata multiplied by the standard deviation of that strata. And we can show that the total sample size is very similar to what was given in the general case, except you can see here that we don't have a variable for cost. So under optimal allocation, we would begin by computing equation 1 here, and then we would use equation 2 to allocate the observations to each strata. All right, so we're going to look at an example of this. Just before I get there, going back to assignment 8, number 2. So if we utilize optimal allocation, we can show that the variance of our estimator reduces to what is given here, and I'll call this equation 3. All right. Now, in this situation, we're ignoring the FPC. So on assignment 2, we can also make the same simplification, and we can ignore that value as well. So effectively, on assignment 2 in question 8, we have under proportional allocation, the variance of mu st is equal to 1 over n multiplied by the FPC multiplied by the sum of WH times sigma squared h. And then we have under is equal to, okay, and then in this case, we're basically going to have the same formula except that the square is in a different spot. So here we can say 1 over n multiplied by the sum from little h equals 1 to h of WH sigma squared h. Okay. So on the assignment, okay, we will ignore the FPC for proportional allocation. And then effectively what we're trying to do here is we're just trying to show that the difference between the two estimators is equal to 1 over n, the sum from h equals 1 to h of sigma h minus sigma bar squared, which would just be like the average of the sigmas. Okay, so the starting point here would basically just be show that the variance of mu tilde st under proportional allocation, so I'll call this prop minus the variance under mu tilde st is equal to 1 over n times the sum from h equals 1 to h of WH sigma h minus sigma bar squared. And then one other thing it'll probably be a little bit helpful. So just because it'll allow you to simplify it a little bit, it'll allow you to simplify on a later step. I would suggest that you write this sum write this as this 1 over n So just let this one run from G equals 1 to H. It doesn't make a difference. It's the exact same formula. It's just a different constant. But there'll be a step later on where you can simplify to get the sigma bar apart. And having this as and then just using the G sum, you can specify exactly what term you're talking about. Okay. But this is the starting point for equation 8. So we're just taking the difference between these two formula for the variance of mu tilde, ST. You can ignore the FPC. And you just want to show that this thing is equal to what was given in the question. All right. Does anyone have any questions? Is the numerator squared under optimal always? Yeah. For the variance term? Yeah. Why wouldn't it be? Yeah, it should be squared. We're talking, so it's a variance. So variance is the square of standard deviation. So if you were to do the weighted sum of the standard deviations, you would have to square that to get a variance estimation, a variance approximation. Okay. Um, okay, so those were the two things I got asked this morning about the extension and that question. So the next topic in the lecture set is just finishing off this idea of sample size calculation and allocation of the observations to each of the strata, or sample size calculation for each strata and overall sample size calculation, however you want to phrase that. But what I just mean is the calculation of little n and then the calculation of little n subscript 8 little h. Okay, so again, under the optimal allocation scheme, we're assuming that cost is equivalent across all strata. So as an illustration of this, we can use the same setup that we had in the example where we considered cost to be varying across the strata. So here we have sigma 1, sigma 2, and sigma 3 known. We have capital H equals 3 strata. We're given the population sizes for each strata. And then we're asked to compute the appropriate sample size and the stratum sample sizes in two different scenarios. So one where sigma 1, sigma 2, and sigma 3 differ across each strata, and one where they're constant across the strata. Okay, so both of these are pretty much just direct applications of the formula that we gave, that were given on the previous slide. Okay, so in the first case, we'll have, so this is for part A, we're gonna have H equals 3. All right, and then we're gonna let, okay, so, oh, it's not written here, sorry about that. Okay, so we'll go, so we're gonna compute the sample size given the different variances. And then for both, let's assume capital B equals 2, okay? Usually the bound will be given to you. I think in this case, it was just a bit of an oversight. So we'll say B is equal to 2 in each case. And then we have our varying strata, our varying standard deviations for each strata. Okay, so and then assume 95% confidence interval. Okay, so we'll start off by calculating n. So that'll be step 1. And then on step 2, we will calculate little n subscript h. All right. So to calculate little n, we're going to use our formula for optimal allocation. So in the numerator here, we'll have the sum from little h equals 1 to capital H of WH squared multiplied by sigma h all squared divided by n squared times b squared divided by z alpha over 2 squared. This will be plus the sum h equals 1 to capital H, and we will have capital N subscript h squared times sigma squared. Okay, so from the question, we are told N1 is equal to 155, N2 is equal to 62, N3 is equal to 93. So that means that capital N is equal to 310. Right. Okay. All right, now in the top part of our expression here, we have the sum of each fraction of the strata fraction multiplied by the strata standard deviation. Okay, so so let's write here. So we'll just write next to this. So the W1 is going to be 155 over 310. W2 will be 62 divided by 310. And W3 will be 93 divided by 310. So here we're going to have 155 over 310 multiplied by 5 plus 62 over 310 multiplied by 15 plus 93 over 310 multiplied by 10. Okay, and then on the bottom, we will have 310 squared multiplied by 2 squared multiplied by 1.96 squared. Okay, and then we're going to have a similar expression in the denominator. So here we will have 155 multiplied by 5 squared plus 62 multiplied by 15 squared plus 93 multiplied by 10 squared. Okay. Okay, so then we can show that the top, and then this whole thing is squared. And then, so then we can show that this simplifies a little bit anyways, to 2,635 squared over 310 squared times 4 divided by 1.96 plus this sum on the bottom, which is 227,125. And that gives us a sample size of 54.59. Therefore, n equals 55.
So why they in alphas you use 1.96 because they didn't tell me it's 5%.
So it's a 95% confidence interval. So alpha would be 0.05. So the Z is on subscript 0.05 over 2. So Z subscript 0.025. The Z score with 0.025.
Also means we always assume the confidence interval is 95%.
Yeah, if it isn't stated, that's the standard.
Okay.
Yeah, the numerator is squared and then 1.96 squared. Yep. Okay, so then now we have little n. So the next thing that we want to do is just allocate these into each of the different strata. So we're going to do this using the allocation constant for optimal allocation. All right, so in part 2, we have calculate little n h. All right, so little n h, actually I'll write that up here. So little n h is equal to ah multiplied by n. Okay. Well, I guess I should put the ah in brackets because that would be more consistent with what was given before. Okay. So this is going to be wh sigma h divided by the sum h equals 1 to capital H of wh sigma h multiplied by little n. Actually, I don't need this, it's implied. Oh, sorry, nh, not w. But in fairness, that would be the same thing, right? Like if you have wh multiplied by sigma h and you have nh multiplied by sigma h sum, the n's gonna get canceled out. So it would give you the same solution even if you kept them as w's. Okay, so then we would have n1, for example, is equal to 155 multiplied by 5. And then that's going to be divided by, well, I guess we need to give myself a little more room here. That's going to be divided by 155 multiplied by 5 plus 62 multiplied by 15 plus 93 multiplied by 10. Same calculation as before. So this is going to give us, let's multiply by n. Okay, so that's going to give us 155 times 5 over 2,365 multiplied by n. Okay, so that'll be 0.30 multiplied by n, which is 17. Or I guess, just in case. Right. Okay, so N2 will be the same idea. So here we're going to have 62 times 15 divided by 2,365 times 55. Okay. So this should give us 19. And then we will have N3 is equal to 93 times 10 divided by 2,365 multiplied by 55. And this also works out to be 19. So therefore, little n equals 55, and 1 equals 17, and 2 equals 19, and 3 equals 19. 8, 7 is 5, carry the 2, 55. Oh, wait. I got careless with space, actually, because I forgot there's a part B here. Let's move this up. Okay. All right. So in part B of the same question, we're being asked to do the exact same process. So we want to use optimal allocation again, but in this problem, we want to use a constant variance estimate across the strata. Okay, so to do this, what we're going to do is we're going to compute effectively like a weighted sigma squared or a weighted sigma hat. So I'll show you what that's going to look like now. All right, so we have one second. Yeah, okay. All right, so the starting point here is to recall the sample size formula that we computed on equation 23. Okay, so just as a reminder, on equation 23, so last class, we derived an expression to compute little n across H strata using our traditional approach for bounding, using our traditional approach, let's say. So that estimate is given here on equation 23. So the starting point here is going to be this expression for little n shown on slide 23. So here, what I will do is I'll start off just by writing, so recall, and this will be from slide 23, that little n is equal to the sum from h equals 1 to capital H of n h squared sigma hat h squared divided by w h, and then this thing is going to be divided by b squared n squared z alpha over 2 squared plus the sum h equals 1 to capital H NH sigma hat H squared. Okay, so we're going to assume a constant variance, right? So assume sigma hat H equals sigma hat for H equals 1 to capital H. So I'll write let to give me a little more room. So each strata has the same standard deviation, I should say, in this case. Okay, so we have a consistent standard deviation for each strata. Okay, so if we make that assumption, then we have the following: 1 over capital N, the sum from H equals 1 to capital H of N subscript H sigma hat H squared divided by B squared N squared Z alpha over 2 squared plus the sum H equals 1 to capital H and H sigma hat H squared. Oh, no H's anymore. Okay. Okay, so there's a couple of ways that we could do this now. So we can just make a statement about what we believe sigma hat is going to be, and we can do a really crude approximation of the estimate, or we could use a weighted average for sigma hat. I'm just going to use a crude approximation for now, just to sort of carry on with the question, because this is taking a bit longer than I thought it would. So we're going to go sigma H is equal to 1 over H, the sum H equals 1 to capital H, sigma hat H squared. So this is going to be 1 over 3 multiplied by, should be 15 over 30. So that's going to be 10. Right? All right, so then we can say, okay, so therefore, or actually we don't need to say therefore. Okay, so we're going to say that sigma hat is equal to 10. Okay, so then this thing is going to become 1 over 310. And then on the top here, we're going to have each of our sample sizes. So 155 times 10 squared plus 62 times 10 squared plus the next value times 10 squared. Right, so this is going to basically just be yeah, I mean, this is going to work out pretty clean. This thing will be 310 times 10 squared. So you can see that we're going to get some cancellation there. And then on the bottom, we'll have 2 squared, 310 squared divided by 1.96 squared plus, and then we have the same expression on the bottom. Okay. And then we should be able to show that this works out to 73.32381. Therefore, n equals 74. Okay, and then I'll just Move this part over here. All right, so then we're going to have n1 is equal to a1 times n. Okay, so in this situation, when we go to simplify each of the expressions, we're going to end up with, well, basically we're going to have the following. So you can see, for example, in the first one, if we take the first sample size, which was 155, and we multiply by 10, and then we're basically just dividing by each sample size, right? So you'll have 155 times 10 plus 6293. Okay. And then what you can see is the 10s get pulled out. So this thing simply reduces to 155 over 310. So you can see now that under optimal allocation, what actually ends up happening is that we just have proportional allocation of the observations. So that's kind of a neat result. So once the variance is constant across the strata, you end up at proportional allocation, right? So then we just have 155 over 310, which would be multiplied by 74. So that would be 37. For N2, we have 62 over 310, which is multiplied by 74, which is 15. And then for N3, we have 93 over 310, which is multiplied by 74, which is 22. And then maybe I'll just punch the 74s in just in case. It's a neat result. Okay. Do you always round up? Yeah, so you always round up with your sample size because the value that we compute, so for example, 73.32381, or the value we computed in part A, so the 54.59, that's the minimum possible value that you can collect to achieve your bound, or to achieve the bound that you have specified. So if we go below 54.59, the bound might be slightly larger than 2. But we want the bound to be exactly 2 or smaller, because if you have a smaller bound, I mean, that's just a more precise estimate, so that's fine. So with sample size calculation, you always round up no matter what the value you compute is, because if you round down, you will miss the bound by, it might be a small amount, but you would still have a bound that's larger than what you specified beforehand. Okay, so we don't want to sacrifice the width of the interval for one less observation. All right, so any other questions? Yeah, so it's the same argument. Like if you round down to 54 from 54.08, your bound is now going to be bigger than 2, or whatever bound you specified. And you don't want to sacrifice that precision for the observation. So even if it's still really close, the rule of thumb is to always round up, because that way you're guaranteed to achieve the bound that you specified beforehand. Any other questions? Okay, so the next topic in the lecture set is what we just talked about was sample size calculation for each strata. We're going to talk about how to determine the number of strata for a particular experiment, though, to be honest, like this approach that we're going to talk about is a pretty, um, it's not the greatest approach I've seen for computing the optimal number of strata. I think that for the most part, knowing how many strata to collect really comes from an understanding of the population and the dynamics of the population that you're studying. Now, again, the main purpose of why we've gone through this study of stratified random sampling is because depending on the population you're working with, the stratified approach can lead to more precise estimates for the population quantity that you are working with. So again, if you just consider the most common case, which is the estimation of a population mean. So we want to say something about the population value or the population mean mu. We have three approaches. We have simple random sampling, systematic sampling, and stratified random sampling. Systematic sampling and simple random sampling, as we saw, are very similar because they use the same estimates. We saw some approaches for dealing with this problem in systematic sampling. So if we have like a periodic population, we can use repeated systematic sampling. And then we can actually use an ANOVA structure or an ANOVA table to build an estimate for rho. And then we saw that if we have an ordered population, we can use difference estimation within systematic sampling to find an estimate for the population mean. And now we have stratified sampling. Stratified sampling separates itself from those approaches because it's breaking the population up into these strata, which are basically just groups. So you can almost think of it as just breaking if you have it's kind of like a rectangle, you're breaking the rectangle up into three different sections, for example. 3 is an arbitrary number. It could be 4 or 5. Like, capital H is typically will be specified, but you're breaking the population up into different sectors or areas or groups, however you want to think about it. And now you're performing estimation within each of those. And if those groups are well separated, but they're very common in their individual structures, the stratified approach can actually provide a better or a more precise estimate of the population mean. And we can say things like this estimate is better, but in our situation, better means has a smaller variance. And that's where the idea of a relative efficiency and comparing the variances comes into play. Okay, so we're going to talk a little bit again about forming the strata, like how to compute the number of strata. After the break, we're also going to talk about some of the extensions of stratified sampling. So these are called post-stratification and double sampling, which are both interesting ideas. And double sampling is really just stratifying after you stratify. So it's kind of cool. It's almost like a bootstrap in some sense. On slide 36, I just give a little bit of a summary of some of the notation that we have seen so far. It is a pretty notation heavy course, so trying to keep it straight can be difficult. But with that being said, I'm going to stop here for today because, there's only a minute left anyways. So you can have until Monday to do the second assignment. And after the reading week, we'll pick up where we left off. The third assignment will be up by that point. We're going to start moving into new topics. So ratio and regression estimation will be the next things we see. And we'll talk about ratio and regression estimation both in simple random sampling and in stratified random sampling. So we're going to have some continuity of the topics that we've already discussed. And outside of the course, I hope that you have a nice reading week and you get a chance to recover a little bit before the last half of the semester. And then, of course, we get a much longer break over the summer. And yeah, so, if you have any questions, I have office hours after this. And feel free to email me as well, or Discord or whatever. And yeah, I'll talk to you guys not this coming Monday, but the one after.